Hi everyone, welcome. This is Dr. Kofelt. I'm going to be talking about acid-base titrations today, which is a fun thing, right? Okay, acid-base titrations are where we apply stoichiometry to acids and bases that are reacting in solutions. So a titration is basically where we take a standard solution, so we know it, we know the concentration of it, we add it gradually to an unknown concentration solution until the reaction completes, and then we can show by how much volume of the known solution it takes to the unknown solution and figure out what the concentration is. So a solution of a strong base like sodium hydroxide can be used as a standard solution, but it's first got to be standardized. So I can use the standard sodium hydroxide to standardize acids, but I have to have what's called a primary standard to standardize the sodium hydroxide initially, because sodium hydroxide can decompose. It actually reacts with carbon dioxide in the water, and so the concentration decreases over time. So I have to, even if I have like a known sodium hydroxide standard, I have to re-standardize it every once in a while just to make sure that it's still correct. And we can standardize the sodium hydroxide solution by titrating it against an acid that I can weigh, so I can know exactly how much I've got in there. One of those that we use quite often is a monoprotic acid called a CHP, which is potassium hydrogen phthalate. And this is a white soluble solid, very purified, because a lot of people use it, and we even will keep it in like a humidor kind of thing, a desiccator I mean, to make sure that no water gets to it. So this is what it looks like. KHP is, as you can see, a cyclic structure, and it is a potassium salt of this hydrogen phthalate molecule. When we add it to that, we do get an aqueous solution and water. And so this is the net ionic equation here. Now, having said all that stuff, okay, it is a monoprotic acid, so it reacts on a 1-to-1 ratio, which makes the calculations a little bit easier. So if you're going to standardize a solution of sodium hydroxide with KHP, you take a known amount, so you've weighed this out, and you put it in an Erlenmeyer flask with distilled water. You add some indicator to that. For example, phenolphthalein we use a lot in acid-base reactions because it is colorless in the low pHs, in the acidic and neutral solutions, but as soon as it gets basic, okay, it turns pink, and it turns bright pink if you go too far. So this is what it looks like initially when you start, and you've got the phenolphthalein in there, and you've got the KHP. It's colorless, okay, because the KHP that's in there is an acid. You carefully add the sodium hydroxide to the KHP solution using a burette until you've reacted it all. And when that is completely neutralized or reacted out, that's called the equivalence equal point. Okay, so you've got equal amounts of hydrogen ions and hydroxide ions is basically what that means. The end point is where the the color changes in the solution. Okay, and so the color change happens if it goes to like more base than acid in there. So at the equivalence point, all the KHP has been neutralized by the sodium hydroxide. It's still colorless, but if you add one more drop of sodium hydroxide from the burette, it will immediately turn pink. So when you're titrating, you see what we call flashes of pink. So as it hits, and usually we're stirring this a lot, okay, to make sure that the reaction is going. But if you keep adding the titrant from the burette to that, then it will, like, you'll see pink where it's hitting the solution, and then it'll dissipate, okay? And so at some point it will turn a very faint pink, and if it goes back within 30 seconds, then you still haven't added enough. In an acid-base titration, you want it to be as light pink as possible when you're using phenolphthalein, because one drop too much and it goes like super bright pink. So in an acid-base titration, the total number of moles of hydrogen ions that have reacted at the equivalence point are equal to the total number of hydroxide ions that have reacted. And so this is what that reaction looks like. So if it turns slightly pink, and it will stay for 30 seconds, then you know that you have reached the equivalence point. So if you all of a sudden it turns this bright pink color, the whole solution, and stays that way, you went too far, because one drop past the equivalence point makes it turn this bright pink. So you have to be super, super careful when you're doing it, and like even put like a white piece of paper under it so you can see that change. But once we've done this titration, as close to just the subtle pink as we can, then we can use the numbers to calculate the concentration of that sodium hydroxide, and then we can use the sodium hydroxide as the standard for other bases. So in a titration experiment, a student finds that 25.49 millimeters of sodium hydroxide solution is needed to neutralize 0.7137 grams of KHP. What is the concentration in molar of the sodium hydroxide concentration? All right, so we have, and this is going to be like a dimensional analysis sort of thing. Okay, so you've got 25.49 milliliters of sodium hydroxide. And we're going to be using molarity. And molarity, if you recall, is moles per liter. So I'm going to go ahead and I'm going to convert this to liters. So there's 1,000 milliliters in 1 liter, right? So it's 0.02549 liters of sodium hydroxide. That's what it takes, all right? The formula weight of KHP, and I gave you the formula earlier, but it is 204.2 grams per mole. So I have and I'm going to use this later, okay? 0.7137 grams of KHP times 1 mole over 204.2 grams of KHP. And the molar ratio, I told you it's monoprotic, so it's going to be a 1-to-1 ratio. Remember the molehill. And so I'm going to have 0.003495 moles of sodium hydroxide. Right? Sorry, because this is moles of KHP to moles of sodium hydroxide. All right, so that grams, moles of KHP, moles of KHP, moles of sodium hydroxide. That's why you do it, so you don't mess up. So you got moles of sodium hydroxide. Okay, to get molarity, we've got to divide those moles by liters. So we've got 0.003495 moles of sodium hydroxide in 0.02549 liters, and that will give us 0.137 moles of sodium hydroxide per liter, or 0.137 molar NaOH. Okay, so when we use this primary standard, that's how we calculate it, because we've got grams. And then here's one for you, very similar to work. So we have to use that primary standard to standardize the sodium hydroxide, and then we can use that standardized sodium hydroxide to calculate concentrations of an unknown acid by titrating with that. And it's easier because it's a liquid already. So I'm going to show you how to work these. You're going to like these better. And I'll just tell you because it's kind of like the dilution formula we had before, but you've got to remember a particular rule about this, because it depends on whether it's a monoproduct, diproduct, acid, or base. Okay, so, and you can do this with dimensional analysis if you want to, but it's much easier to do it with this formula. So the formula to calculate a titration is N sub A, M sub A, V sub A equals N sub B, M sub B, V sub B. What's that mean? N equals the N sub A equals the number of hydrogens in the acid. N sub B equals the number of OHs in the base. And then M equals the molarity, and V equals the volume. All right, so for this one, I've got 46.3 milliliters of a 0.203 standard sodium hydroxide. So that's my base. And it's neutralized 25 milliliters of a sulfuric that I don't know. So that's the A. All right, but I do know the ends of these because I know the formulas. So that's very important. All right, so, and it doesn't matter like the coefficients. It's the formula that we're going by. So sodium hydroxide has one hydroxide in it. Sulfuric acid has two hydrogens, okay? So my N sub A is going to be 2. My N sub B, number of OHs, is going to be 1. So 2 times the molarity of the acid, which I don't know, okay, M of the acid, times the volume, and I can use milliliters as long as I use milliliters for both. So milliliters of the acid was 25, and don't get them mixed up. You got to be really careful about which one is which, and so you might even want to write that down: 25 acid, 46.3 base, whatever. All right, and then that's going to be equal to the base side. We had 1 hydroxide times 46.3 milliliters of the base times 0.203 molar of the base. And then I'm going to solve for M sub A by dividing by 2 times 25.0 to both sides. Okay, which gets rid of, so M sub A, the molarity of the unknown molarity of the acid, is going to be 1 times 46.3 times 0.203 divided by 2 times 25. Remember, if you're putting those top numbers in and then dividing by 2 times 25, you've got to put that in parentheses, or you've got to divide by the 2 and then by the 25. Okay, that way you won't mess up your calculations. If you do that correctly, the molarity of the unknown H2SO4 is 0.188 molar. We use 3 significant figures. This is a count, so they have an infinite number. So 3 significant figures is what we had. So again, you can do this by using dimensional analysis and canceling the milliliters and the moles and all of that. But to do that, you have to have the balanced chemical equation. If you don't have the balanced chemical equation, you don't need it to do it this way, because you know that there's 2 of those and 1 of those, and then you just need the milliliters and the molarity. Much easier. Okay, so that's how you do titration calculations. Here is yours. There's a standard KOH solution with sulfuric, and then in the bottom one it's got barium hydroxide. Notice it's got 2 hydroxides and 1 H in the HCl. And that concludes chapter 4, our aqueous solutions.